But here we are, second Soccer-Bot workshop. We're talking about hardware and the hardware of the Soccer-Bot. Before, I used to include like learning about the breadboard, learning about a little bit of the remote like receiver, stuff like that. I'm gonna focus just on how we power the motors because if you want to do stuff with your ZoomBot kit, picking up a motor driver will be pretty easy. You can find them on Amazon and picking up motors as well. And then for stuff with like the breadboard, we have ZoomBot tutorials on that one, so you can reference those. So let's jump in here. Here's the stuff we'll talk about. First, we'll hit DC motors and Arduino. We'll talk about how do we use them with Arduino, what's the issue there, because there's a pretty big issue there. Then we'll talk about the motors that we used to use in Soccer-Bot. We'll cover those before we go like, okay, how are we going to use those? Then we talk about the motor driver as well, because you want to match your motor driver to the motor used. Then we're going to go over how a motor driver works, because it's kind of a cool thing to look at. It's a simple scheme, but it'll be interesting to see how it does what it does. We'll go into wiring that motor driver, which is called the L293D. That's the chip name. We'll see how you can wire it, and then we'll use a little online simulator to actually test how it should work. So we will move on here. All right, I'll take a drink, and then we'll cover the slide. All right, so DC motors and Arduino. So if you have an Arduino, you kind of have the idea that the Arduino's little pins, let's say on the right side, they turn on and they turn off through the code that you write on it. So you could say, why not just connect a motor to that digital pin? If it turns on and off, then I could turn my motor just on and off with some code. Well, the issue there is that DC motors draw way too much current. If you connected, in the little picture, if you connected your DC motor to your Arduino and you gave it power, it would fry the chip completely because your Arduino can source 40 milliamps from those little pins on the right side. Actually, I guess I can point this way. Yeah, there we go. If you connect to the little right side there, only 40 milliamps max. If you connect a DC motor though, that motor wants to draw like around 600 milliamps on the average. And then, we'll talk about it later, at the most like over 1 amp. So if you fire up that motor, you're going to fry the chip. So we have to do something about that. How do we give the motor power while protecting the pins? So we have a motor driver, and that's what its job is it takes in commands from the Arduino, but it takes power from somewhere else, so that as we protect the Arduino while controlling the motor. Have any questions with DC motors and Arduino real quick? Question check. Nice. All right. So now here's the motors we used before. We'll talk about what we used to use so that as when we move into the motor driver itself, we'll know kind of what's our baseline. So the DC motors we used, or I'll talk about DC motors first. I almost skipped the second part. So DC motors, they usually only have two terminals, which is kind of like a high and a low voltage. The terminals are also reversible. So if you, let's say, wanted to go in one direction, you connected like high and low like this. If you swap those around from high to low instead to low to high, you can actually just turn the motor the other way. Now, DC motors have lower precision because they're not as advanced. They don't really have anything on the inside controlling them unless it has like a little hub on top of it. But usually, DC motors don't have anything that actually control them. Now, if you had a stepper motor, I referenced that here. Stepper motors are totally different. So a DC motor is like you power it, it goes at its speed depending on the power. A stepper motor is a thing that will move in an increment. So if you have to send it like move one step and it will turn like one step like this. Kind of like a servo, but it keeps rotating. So for stepper motors, those ones are going to have more accuracy because you have full control of all the steps, but they're much harder to drive because you need like a little encoder and stuff like that. So for Soccer-Bot, you just kind of want to drive around. We can use DC motors. And then, like I said, they're easier to utilize because DC motors just kind of like a direct control. Stepper motors, you got to use a little bit of like an interface and like a library. So for Soccer-Bot, the standard we use, they're called N20 DC motors. I should have put a little picture on screen actually, but let me move it in front of my face here. So here is the motor. It's a very small, yeah, there we go. It's not going to glare. So it's a very small little DC motor. It's got a little gearbox on the tip to give it a little bit of a gear drive and lower the RPMs. They're very small, but they're actually pretty strong. I remember when I first bought these for Soccer-Bot, I was like, these can't have hope of driving your Soccer-Bots. And it's actually pretty good. They're not super strong, but if you need more strong, you can change the RPMs. So that little motor is 6 volts, so it's driven by 6 volts. The little gearbox on it has it for 300 RPMs. And then here's the interesting part. 70 milliamps it takes to drive it with no load at all, but 1.6 amps if it's fully stalled. So like let's say you got your Soccer-Bot and you drive into a wall and you're still like hitting the gas, these things will draw a huge amount of current. So even with the no load, that's still technically too much for those Arduino pins and you would burn them. So that is why we need that driver. Any questions on the motor real quick? You good on motors? Nice. All right. So the motor driver that we chose for the
Wait,
project.
sorry, can you repeat? Wait,
Oh yeah.
can you repeat about what
Oh, I heard you lag out.
breaking? I keep breaking out. Yeah, internet's not good.
Oh no. If you want here, if you could type it in the chat, if you got keyboard access, I'll answer it for you just in case you're lagging. All right. I'll read it for the recording. So Jake asks, can you repeat what you said in regards to the N20 stepper and servo motor? Okay. So, and actually since you're mentioning stepper as well, or sorry, servo. So you kind of have like three range of like introductory motors, you can say. So I'll cover those three because I think we'll have a good time with it just being a small group here. So first you have the DC motor. You can think of a DC motor as like part of the other motors, you could say, but the other ones are more advanced. So DC motor is, I've got the motor here, and it's got these two little pins on it. It's as simple as you connect your power to these pins, and this motor just goes. That's all there is to it. There's no fancy control with it. It's more of it's on or it's off. Depending on the voltage, it's going to go faster or slower. Uh, and then there's a little bit about PWM later, but we're going to save that. Possibly we can save it for the end as well. Now, for the stepper motor, a stepper motor is kind of like it's got a motor. I actually have one too, and I should have brought it so I could show you. But a stepper motor, it has like, let's say 5 wires. And what that one asks for is you could say it kind of looks like a gear. It's kind of like a cog. And what it does is like, let's say you turn on, you send a signal to rotate what I'll call one tick. The motor will then, it'll do like, I turn this guy on, I turn this one on, this one, this one. And it does this pattern, and then it goes whoop, and it rotates one tick. And then you send another one and say, okay, I rotate one more, rotate another tick. And then so it kind of moves in ticks. A good way to think about this one is like with robotics, like if you have robotic arms, they're going to use stepper motors because they need to be precise. You have, you could say, 248 ticks, I think is like kind of an introductory one, like 2048 ticks of control on your servo. So if you know, like, hey, one tick moves like 1 degree, I want my arm to move 90 degrees and then come back. You could program it to say, hey, send 90 ticks to that motor and it will move 90 degrees. Reverse that, send 90 ticks the other direction, and it will go perfectly back. You can think too, another good use of stepper motors is a 3D printer. A 3D printer needs to be accurate because they need to print so perfectly. So if you're trying to do like a design, your stepper motor is going to handle like, okay, move the nozzle from this corner to that corner. And it does like some math and says like, okay, well, to get from here to there, that's like 100 steps for one motor to move it this way forward, and then 100 steps of the other motor to move it this way to the corner. Stepper motors are accurate and they're pretty good. They can use some power though. They heat up. You got to be careful. I did not know that they heated up as much as they did. And I had a lamp, or I had a table fan that I made that oscillated with stepper motors because I was learning about it. It got so hot, it melted my hot glue. It fell, it shorted, and I was sad. It broke. It broke things. I did not know that they heated up. Uh, so that's stepper motors. They're very accurate. They need a specific little controller. So kind of like how the L2, or we have our motor driver here, is for DC motors. You don't need a motor driver for DC, but you do need a controller for stepper motors because you need to send it like, okay, this command or something like that. You need to send it something specific for it to actually toggle in the correct way. Otherwise, if you don't do that, your stepper motor will actually just stutter like this in place and it'll be stuck. It'll look like it's stuck. It's because it's not getting the right signal. And then lastly, servo motors, it's kind of like an in between. They're powered off of DC motors, uh, but they will usually have like a sensor inside them that it kind of keeps track of its position. So it has a little tracker that says like, okay, I know that I'm vertical like this. Here's like here's where the shaft is at my wrist. I know that I'm in this vertical position, and then you send it a code similar to like with a stepper motor. I want it to be like turned all the way this way. And then it has a little tracker in it that says like, hey, you're at 90 degrees. I want you to be at 180. Please turn to one, or please go to 180. So then it'll go and it'll actually rotate. And then it will try and get back to that position. So I would say for simplicity, DC motors kind of comes first. You could just directly power that thing and it goes. Servo motors is kind of second for uh, half complex. We're usually like with a servo motor with Arduino, it's just like you just connect the one wire to like a digital pin, and then it sends the code to drive that pretty easily with PWM. Actually, it uses PWM to determine the angle. And then lastly, the stepper motor, very fine control, very strong as well. They're a little hard to rotate on their own, but you're gonna need more advanced little controls to actually determine like what position it is. Is that a good clarification on motors? That's a good question because a lot of people they asked me for Soccer-Bot as well. Like, are we using like what type of motors are we using? Because they've only known about like steppers. I was like, oh no, steppers would be complicated and they'd be slow. Oh, that's a good point. Stepper motors are also kind of slow. They can be a little slow depending on if they don't have like the right gearbox. So
Yeah, I
how's
got it. Thanks. Thanks.
no problem. Thank you for the question. All right, let's see here. Let me go back to this. All right, so we're focusing on the DC motor because that's what we had for Soccer-Bot. So we talked about motor drivers before. That is the solution to our issue. We can't connect our motor directly to an Arduino because we're going to fry it. So this is our solution. So if we consider, we have 1.6 amps max draw per those 6-volt motors. That's kind of on the data sheet. And we're going to have 2 of those motors on a robot because you can have one of just like one driving motor, but Soccer-Bot's just been 2, so that was you can kind of like pivot based off of what direction that you spin it. So the chip to use, we will utilize the dual H-bridge motor driver, the L293D. There's that picture of it right there. And then once again, here's the perspective of it in real life. It's pretty small. It's only 8 pins on each side, so it's easy to fit. I have my old Soccer-Bot here that's like kind of disassembled. So like the ZoomBot kit comes with like a large breadboard. In perspective, like you can use, there we go. You can use like a pretty small one. I've got these small ones like this, and it like easily fits all the stuff on there. So it's pretty convenient, nothing too big. There we go. So here's the stats on this chip. So the L293D supports motors from 4.5 volts all the way up to 36 volts, so we're easily in the clear on that one. Another cool thing is it has separate motor control for 2 motors, so you can say with the chip, one half of the chip controls, let's say, the left motor, and the other half of the chip controls the right motor. Perfect for us. Also, it allows for reversible motor direction, which is great. So let's say your Soccer-Bot drives into the wall. If you can't back up, that might be a little difficult because you gotta like wedge yourself. This allows you to reverse the direction and go backwards. And then lastly, we have the 1.2 amps peak per channel, which is 600 milliamps average. Oh, you know what? I gotta ask. Did I go over this slide already? I didn't, right? Because I was
Don't think
reading
so.
this. Okay, sorry. I think I had a moment where I was thinking of my practice, and I was looking at this line, and I was like, I didn't already explain this, did I? Okay, we'll strike in reverse. So 1.2 amps peak current possible per channel, 600 milliamps on average. So it's not the full current load of 1.6 which would draw, but I mean, I would just advise don't draw that in the first place regardless. So like I would tell people when we are building Soccer-Bots, like, hey, try not to drive the Soccer-Bot into the wall because it's gonna do a little damage if you're driving into the wall and like you're still forcing the motor to run. It does hurt. You can heat up the motor driver pretty quick. But on typical load, the capacity of this thing is going to be pretty great. All right, any question on the motor driver here? We'll be going into like how to wire it and the pins and all that stuff. But any initial questions? Seems like we're good. All right, so now we'll look into how the motor driver actually works. So this one's a little cool. So the H in the H bridge, because previously I said it was a dual H bridge motor driver. So the H in the H bridge has an important function. And what it does is it allows those motors to be reversed based on the certain channels that you open up. And then also I have a little picture of a battery here. So the good thing about the H bridge is it can route the power from another power source, which would be like a battery pack, while being controlled by the Arduino. So that's the good part. And here's a little GIF that we'll look into on the next slides, but you can kind of see, like, depending on which one closes and opens, you can see the motor turning in different directions. So let's jump into that. All right, so we'll look at the first kind of state. So here's your motor driver. Let's say you have everything hooked up. No gates are open right now. The Arduino has not told any of them to close. So motor's off. Motor's not doing anything. Then what we do is, let's say we close the top left and the bottom right gates where those arrows are pointing. Now current is ready to flow from the top left where that red wire is, down through the motor and then into the black wire at the bottom there. And then we can see that here. So now we can see current's flowing from top left to bottom right, and the motor, let's say if we think of it kind of like water. So if the top area is filled with water, that's falling down, it's going through. Our motor's kind of like a water wheel. The water's going to go over the motor, push it, and it's going to make it turn clockwise. Then the water's going to keep going, it's going to come out, it's going to go through the bottom, and then it goes technically back to the battery. So by closing top left and bottom right, now we have a circuit to where the current's going to flow. It's going to turn that motor in one direction. Then, let's open them all back up. So there's a frame in between here. We open up all the gates. Then we close the opposite set. So now we're closing top right, and then we're closing bottom left. So we do this, now current is ready to flow in the other direction. And then, here we go. Now current's going to flow top right, bottom left. It's going to rotate the motor now counterclockwise. So here's where the H bridge comes in, is it's kind of got that H shape in reference. Based off of which legs of the H you control, you can make the motor change direction. And then obviously, like, you can't open like both the top or both of the bottom, because then it's not going to do anything. There's not a circuit there. So it has to be kind of toggled in between the two. And then the pins on it will say, like, let's say, like input 1 and input 2. So like if you power input 1 high but input 2 low, it's the same thing as opening top left or closing top left and bottom right. That'll do that sort of thing to give you that power flow, and it'll rotate your motors. So how does that feel? Does the idea of the H bridge make sense? Seems like we're good. Nice. All right. So now, for wiring up our motor driver, because now we've got the concept of how it's working on the inside, we can see that power is being routed through those channels. Based off of those channels, it's going to change the direction of the motor. So, your motor controller is split down the middle. I kind of referenced this before. The left inputs and outputs for the left motor are on the left of the chip, mostly. And then the right I/O for the right motor is on the right side. So it's kind of convenient to where if you want to, let's say, wire up just the left motor for some testing, you could just focus on the left side with like a pin or two extra that you need to hook up. Then you also have these enable pins. So what these do, you set these high or low, and it will enable or disable the motor entirely. So this is kind of like, I don't know how they work. Like, well, no, I'm not going to use the light switch example. So let's say you had like a cutoff switch for like a whole circuit that you have. This enable pin is like a cutoff switch. So if this one isn't turned on, you could say, your motor, even though you set it to go like forward or backward, it's not going to do anything. It's got to be enabled or disabled in order for it to be actually working. Now the other thing is with PWM, if you tell this little gate or this enable pin to turn on and then turn off with pulse width modulation, that's how you get your speed. This is kind of like an LED. If you turn on and off your LED quickly, multiple times a second, then you get that dimming factor. So depending on how quickly it is, or how much more on it is than off, let's say you see your LED brighter. If your LED is a lot of it, I have to word this correctly. If your LED is off most of the time, it's going to look much dimmer versus if it was on most of the time. You could do the same thing with these motors, so that way your Soccer-Bot isn't just like, I go forward at full speed or I go backward at full speed. You can kind of have a little bit more fluid direction if you want to make like a smoother turn, or maybe you don't want to run into somebody by accident, maybe it's a teammate. These enable pins allow you to control the speed. Then we have our direction pins. So these ones control the gates that open and close the H bridge. So you're going to set these high or low, and based off of what you do there, it's going to enable those little things on the H to either drive the motor forward or drive it backward, as long as the enable pin is set to high. Then for other pins, we have our output pins. This is just where you hook up the motor. So the output pins on the chip would be connected to these little tiny plugs on this motor here. And then the last ones to note are VCC1 and VCC2. So this is kind of what we mentioned before, is we have power sources for the motors that kind of bypasses the need to get it from the Arduino, and then also the chip needs power. So VCC1, which will be at top right, and we'll look at that for sure. That one powers the chip itself because the chip is logic. This also needs power just to do work in general. So that is for this chip. But then also in the bottom corner, that's where, like, let's say you plug in your batteries. It's a rechargeable, it's a whole bunch of double A's. There are two power sources going into this one, and it'll be important to make sure that they're the right one. Because the VCC1, it needs logic power, which is always, or usually it's 5 volts. And then the bottom one would be whichever power you need for your motors, which in our case, it would be 6 volts. Let's see. All right, now we will move into the actual little diagram here for the L293D. So there's a great resource online. It's called Tinkercad that I didn't know that it let you do this. I found this out yesterday, that it has a little motor driver. So I was like, you know what? We're going to make use of this, and we'll show the motor driver on here. So you can see you got our here. Let me go to the PowerPoint. So yeah, we can see the mouse. Nice. All right. So we have our Arduino here on the left, and I'll lean this way. Oh, I was going to reverse the camera so it looks like I'm looking at the screen. But I have a Arduino right here on the left. We have a little battery pack here on the left as well. That's for our motor power. And then we have our breadboard setup with the L293D in the middle and two DC motors at the bottom. So with controlling, our Arduino is controlling the chip, we would be able to route the power from the batteries into these DC motors. And then we'll look at the chip here itself. So mentioning before, we had those enable pins. We can see those in top left and bottom right here. Those are the ones that will be enabled and disabled to control all the motor, and you can also regulate speed. Then in orange, we have all those input pins. Let's say input 1 and input 2, those control forward and backward for the left motor. Then you have output 1, output 2. Those are just power connections for the motor, the left motor. And then we have ground pins here. The ground pins are just to return all the power that you use because the power's always got to go somewhere. So ground pins would connect and return back to the batteries. And then we have at the bottom here, here's VCC2. At the bottom, this is where the batteries would connect. And I'll zoom in on the actual diagram so we can see kind of the wire, how it goes. If we move to the right side of the chip, at the top we got VCC1. This is chip power. So this one, if we look at the diagram here, there is a red wire coming from the 5 volts of the Arduino, and it plugs into this plus rail on the right, and then that jumps the gap here and goes into the chip itself. So that is logic power. Then we have inputs 4 and 3. Those control forward and backward for the right motor. Then we have output 4 and output 3. Those control, or those are just hookups for the other motor. That would be the right motor. And then we have our grounds again at the bottom, or sorry, in the middle. I was looking at the enable. Grounds again at the bottom to return. There are 4 grounds here, and the reason why there's 4 grounds is just because if your motor is drawing a lot of power, you're going to need more than one little tiny leg, because you can kind of see here if I can rotate. Yeah, the legs are pretty tiny. They're chips. Legs are very tiny, and if you have motors that are, let's say, using that full power, it's possible that the little legs are actually going to heat up because it's too much for one leg. So if you're going to use that, make sure to connect all the grounds. It's always a good idea to just connect all the grounds, because if they put them on there, it's probably for a reason. So let's see here. Is this Tinkercad? All right. Let's go to Tinkercad and let's take a closer look at our circuit here. All right. So I constructed this in Tinkercad, 1 minute thing for Tinkercad. So Tinkercad is something from the Autodesk company, to where it lets you build circuits. They have, like, you can kind of see in this little bit of a preview here on the right, you can see they have all sorts of parts that you can drop in. So like, let's say if you're trying to do stuff for Zoombot and you want to work with your photoresistor, you can actually build a circuit that has a photoresistor in it, and you can like tweak how much light it's getting, and you can see what it would do with your system before you actually even build it. It's super cool. So let's zoom in here on our chip so we can see how to wire it. It's a little daunting. There's a lot of wires, but like once you kind of see how it flows, it kind of makes a little sense. So we'll go ahead and start here at the top of the chip. So we can see here we have this orange wire. I've colored the orange wires to be the enable pins, which, yeah, okay, color looks good because it looked kind of funky on my PowerPoint. I noticed this one looked orange. Orange pins are enables. Those ones I'm connecting to these pins 5 and 6, and if you notice, 5 and 6 has a little squiggly line because the pins on the Arduino with the little squiggly lines on them are pulse width modulation. So if we wrote the code to output pulse width modulation to this top pin here and this bottom right one here, that would also control the speed. So that's why we use 5 and 6 here. So there's our enable pins hooked up. Also, we can oops, I don't want to draw a line there. Hold on. Can I pan? There we go. We can also see that our chip is placed in the breadboard across the middle. That is also an important part that I should have put on the PowerPoint. This chip is connected across the middle divide. And that is because if it was not placed across here, let's say the 5-volt power is also going to be connected to the enable pin. So technically, your motor is always going to be powered on because the two pins are shared. You don't want that. You want things on the left side separated from things on the right side. So that's why we have our placement right here along that ridge. So enable pins in orange. Then we have input pins are going to be in pink. So I routed them just around this to get around the other side, add some cleanliness. So we can see the enable pins for the left motor, if we look at the left side, are right here and right here. These ones are just connected to pins 8 and 9. Pin 9 is connected to a PWM pin, but just because it is a PWM pin, you do not have to use it. So we're just using it just as a normal pin, high or low. We just want it to turn on or turn off. So that's the inputs here on the left side. Then we have our motor output pins in blue. You can see those going down here to our motor right here. That just connects. Doesn't matter which terminal you connect to. Just know that you can remember which one they are. I have wired my Soccer-Bot multiple times, and it's very frustrating when either the motor is wired backwards or like I have the pins set backwards for the input and the output, and I like keep swapping around. So if your motor's going backwards, you can make the decision, flip the pins here, maybe flip the input pins, change the code, something like that. We got our ground pins in the middle. Those are connected to a ground rail here on this little breadboard. All these grounds are connected together. And then we have our battery power here in yellow. So let me look at the battery pack here. So our motor was a 6-volt DC motor. So for a battery pack, I've got 4 AA's here, 1.5 volts each. We're going to take that power, and then we'll make it convenient. We will use this left side. This was my strategy when I taught it in person. Let's use the left side of the breadboard as the kind of power source for batteries. So if you need anything related to battery power, you tap that this left plus column right here. Grounds are okay. Grounds, as you can see down here, it's connected to the other ground on the other side, which I'll get into in a second. One thing to always know, ground is usually always ground. There is one ground. It is a single ground, and it is always the same. So if you have grounds on your chips like this, and then you have grounds on the Arduino as well, like let's say over here on the chip, over here at the corner as well, those are all the same, usually all the same, and they should be all the same. If they're not, you might have a weird circuit going on. So, battery pack connected here. Yellow line is hidden by this wire. I'm going to move it out of the way. Let's do this. There we go. All right, yellow line connecting right here to this rail. This whole plus column is battery power. It's only 6 volts. I'll move to the other side here to finish the example. So then we have our other rail. This one has a wire going here. This is all connected. Oops, I did not want to drag that. There we go. This is all connected to the same thing here. This is going to be our 5-volt rail, and it's 5 volts because it's connected to this wire, goes all the way over here, and we're tapping the Arduino's 5 volts right here. So this column is 6 volts. This column here is 5 volts. Now, another thing I've done here, it doesn't make sense in the circuit itself, But I have a yellow wire here coming from the battery, and that is going to the Arduino's V-in spot right here. And the thing with this is, like, it'll technically connect with USB power if, like, you were to run the code, all that stuff. But for your Soccer-Bot, like, you obviously don't want to be tethered to your PC or whatever you're programming with, so you want to take that cable out. So your Arduino is going to need some power. Well, the cool part about having the battery pack is if you have this here, it's stuck to my cursor. If you have this here, you can connect this rail to V-in. So not only is your battery pack powering the motor driver to power your motors, it's also powering the Arduino itself. So that way you can kind of kill two birds with one stone on that one. Some people said that like 6 volts on their Arduino was like too low. I've never had that issue. I don't know why. I don't know if I've just gotten lucky and I've never had an issue with 6 volts. They recommend for the Arduino, for this little V-in, it should be like 7 to 12 volts is recommended. Its maximums are 6 to, I think, is it 14? It might be 14. I have the idea of 20 in my head, but that sounds like way too much. I'm not sure where I'm getting 20 from. But I would say 6 to 12, or sorry, 7 to 12 is your average. We should be okay with 6 volts. You know, if you have any issues, then technically you can add another battery. And it shouldn't do any damage to your motors. But battery pack hooked up here, ground's connected. Now if we move to the right side, here's the 5 volts again. We're on that 5-volt rail that is connected to the VCC1 of the chip. That one, it just powers on the chip in general. If you don't do this, then the chip kind of doesn't know what to do because it doesn't have any food to actually turn on. It won't be able to do any of its logic. So we got to power the chip itself. Then we have pink again for the inputs of the right motor. That'll change the direction of the motor. We can see those right here on 10 and 11. Then we have green for our 2 outputs for the right motor right here. We got more grounds again. Just want to use those grounds while they're here. And then here at the bottom is again our enable 2 for the right motor. And this is technically, now we don't have any control of the like actual, we don't have any control of the control. We don't have like a remote control hooked up to this. So like you could put in inputs like with the controller and it would change this. That would be a little bit later. I wasn't sure if that was going to fit. So I was like, you know what? We'll save RC for a different workshop. But this is technically all you would need right here to get, let's say, an autonomous driving robot working. So imagine this. If you had your ultrasonic sensor, which actually, it's hidden. There we go. If you had your ultrasonic sensor hooked up on a little setup right here, and you had this whole thing on wheels, you could create a robot that uses the ultrasonic sensor, it points forward, and it drives until it detects something in the way, and then it makes it back up, it rotates a little bit, and then it goes around and tries to avoid it. With this setup right here, you could totally build that sort of robot because you've got your power routed here for your motor. That's going to pipe into the Arduino as well to power that. Your ultrasonic would kind of be like your input. The code inside the Arduino would be what determines if these pins go high or low. To, let's say, change direction, even change speed, something like that. Maybe like your robot, it goes faster the larger the distance it detects from an object. And then as it's getting closer, it starts to slow down so it doesn't impact it just in case. But this is technically all you need for a little autonomous robot. Any questions on the circuit layout before I hit the little run simulation? Any questions on the layout? It's a little dicey if you haven't seen circuits before. That's why, you know, it's one of those things of like, if it's in person, you got the wires in your hand, you can like plug it in, you can see where it goes. I do like the cleanliness of this because I gotta say, if you do this in person, this is going to be much messier than if you did it in this little diagram. Just like showing my Soccer-Bot here. Like you can kind of see, hold on, like the mess of wires coming off the top of it to get like the motor driver hooked up and all that stuff. There we go. All right. If you got no questions on motor driver layout, I will hit the simulation. Let's see, let's start it up. So for the simulation, I'll check the code. Let's see. It's a little cut off, but you know, there's enough of a window. So this is code that I wrote, and technically this is what we'll get into in the next workshop. We'll actually look at how, like, let's say we did all this, and what's the flow of how to make a robot that will change its motor speed and set like all the pins. But I wrote this little bit of code here to do a little demo. So what's going to happen is if we look down here at our motors, let's see, set 0. So we can see this motor is now spinning, let's say left. I tell it to stop, and then it's spinning right. And then now I told this one to spin left, and then now it's spinning right. So I'll look at the code here to get a little preview. So we'll ignore this for now. We'll pretend we're not going to look at any of this. We'll go into the loop just to see like what we're doing. So the first thing we do, we're not doing any speed control right now. We just want to turn on. So those enable pins that we talked about, the ones in orange, right here, we're setting those to high. We want those on. So we're saying orange wires, turn them on. Then we want the left motor to spin. So what do? We have this forward pin, we set it to high, and the backward pin we set to low. So the forward L pin is this pink wire right here. Let's see if it'll let me highlight it. It's not letting me highlight it, that's rude. But forward left pin is this top pink one. And then backward L pin is going to be this bottom pink one. So I'm setting the top pink one to high, the bottom one to low. So that is telling the motor, okay, you have the pins set up this way. That means you're going to spin in a specific direction. That is telling those gates from the H bridge of like, let's say, if I powered this one high, that means like open top left and bottom right. I powered this one low, that means, or sorry, not open. Close top right, bottom left. Other one is powered low, open bottom left, top right. Then here I turn it off. So to show that I wanted to turn it off, what we do is we just hit them both with a low, like this. So before it was high, now it's low, so it's going to stop. Then I want it to spin in the other direction. So if you want to reverse the direction, it's as easy as before we said high and low here. Now we're having it go low and high, just like that. Oh, and I hope I wasn't actually cutting it off. You let me know if you need to see the code again, just in case it was like behind my camera. It might have been with the scroll. Oh, and I can't, I can't toggle off the camera, but I'm trying to think if I can like hide it so I can show you guys the bottom here. Maybe? Let's see. See if I do this real quick. There we go. There's a bar in the way, but you can kind of see through my weird video border. All right. So we have now the left motor is spinning right. Let's say we have reversed the direction by reversing. This one was high, now it's low. And instead now it's the other way around. Low, high. Now if we want to make the right motor spin, we basically do the same thing that we did before. There we go, get in the window. Now we're talking to the forward R pin and the backward R pin, and we're going to set it to high and low. This will make the right motor spin. And then if we want it to go in the other direction, we just reverse low and high like this. And then we turn both of them off right here by setting everything to low. So it's a little peek at the code. I'll go into it in much more depth later to actually explain it. But in doing so, we can kind of see the pattern of they're both off. Left motor spins to the left, turns off. Left motor spins to the right. We leave left motor on. Right motor now spinning left. Right motor spinning right. And then they're both off again. And it might be a little hard to see the numbers, so I'm going to zoom in. Super zoom. There we go. Now it's spinning right because it's a positive number. Spinning left because it's negative. Spinning right because it's positive. Both of the motors are off. And it's super cool that we can simulate that in this. So, with the virtual environment, this is unfortunately a little bit of the best I can do to kind of show it to you. Let's get that back on. Boot up the camera. Nice, there we go. All right. There we go. Do we have any questions on the simulation part of that? Is it confusing at all how that works? If I can elaborate on any of those aspects, please let me know. Main thing to take away for sure from that is that there's the inputs that control the direction, and those are whether it spins forward and backward, and then there's the enables that control the speed. We'll get more into the speed later, for sure, but yeah, the L293D, it's a cool little chip, and it's pretty inexpensive. At the end of the workshops, I want to kind of prepare like a little bit of a link so that maybe like you can look at a motor driver online and maybe find a chip that you want to buy, as well as like a couple motors as well. Because Zoombot kit is great as a baseline. It's definitely a kit that if you're curious on what's in there and you want to take it somewhere, it's got parts to help you do that. And then you can buy stuff like, oh, well, I'm going to pick up a little motor driver in a motor so that as I can control motors, stuff like that. So let's go back to my presentation here. All right. There we go. Now, let's see. Anything else here? So I gave a little preview of the code. Wasn't a great preview. It's because we're going to look into that in more detail. We'll go through like a little flow chart. Because one thing that when you're coding is really helpful is have a flow chart and say like, what do I need to do? First, I got to get the inputs, let's say. Then I got to take that input data and I got to map it to something to work with it. And then with that mapped stuff, I got to actually output that and do something with it. We'll walk through that with the process of what your Soccer-Bot is going to do. So that's going to be covered in the next workshop. And that covers all of the content for our second Soccer-Bot workshop. Do we have any other questions on the Soccer-Bot content? Anything that's a little confusing with the stuff, or just kind of like circuit stuff in general related to this? Do you have any questions? Do a final check, see if there's any points that I missed here. It seems good. All right. If we don't have any questions, I think that is good for our workshop. So that kind of gives you a little bit of an understanding of a driving robot. It's not too complicated. It's kind of like a toy RC car. You know, you buy when you're kids and they're great to use. And nowadays, like with a little bit of Arduino, just a little motor driver, and you pick up 2 of these kits, you know, you mount it to like a cardboard chassis, and you can build a little RC car on your own.